I'm now going to explain mathematical induction. It's a method used to prove that a statement is correct. For example, here we have a statement that says that 2 plus 4 plus 6 plus up until any number is equal to, and this is now the formula to work out the sum of a number of terms of the series on the left. For example, if you look at the first three numbers here, it's 2 plus 4 plus 6, and that's 12, and you replace, well, we've looked at three terms to add three terms together, and it's 12. So let's see if this formula works with this to describe the sum of the terms of the series on the left. Well, if we replace 3 in there, it's 3 plus 1, and that's going to be 3 times 4 is equal to 12. So it works definitely for 3, okay? But our question is, we need to prove that this formula works for all or any numbers in this series. Okay, and it works for all n, and where n is an element of natural numbers. Now, that's natural numbers. Remember, natural number is a 1, a 2, or 3, and so forth. Okay. To do this, to prove that this statement is correct, you take 4 steps. Step 1, the first 2 steps are easy, and actually the 4th step, it's the 3rd step that is difficult. The first 2 steps, you just need to just go through the motions really. So first of all, we need to see if it works for n equal to 1. So let's say if n is equal to 1, what will happen? Well, on the left hand side, this is now this one, this one, the 2 plus 4 plus 6 up until 2n. If we replace, if we look at the first term is just 2, okay? And on the right hand side, if we replace 1, there's 1 plus 1, and that's equal to 2. And we can see where the n is 1, the left hand side will be equal to the right hand side. So we know the statement is true for a natural number n is equal to 1, true for n equal to 1. Okay, now let's look at step 2. For step 2, we are going to look at a natural number k. Okay, so you say you accept it is true for a natural number k. So that means where the n is equal to k. So you just replace the n with k. And how will that look like? Well, it will look like this. I'll just maybe write it there in yellow. It will look like this then. It will say it's 2 plus 4. This is your original series, 6, and you continue up until 2k, not 2n but 2k, okay? And then on the right hand side you'll just have k and k plus 1. So you just replace the n with k. Let's look now at step 3. Okay, now this is the more difficult step. First of all, what you do is you want to see if it works for k plus 1. So let's look at where if n is equal to k plus 1. Okay, now start with the right hand side. This is always the best to start with the right hand side, and you'll see now why. So in the place of n at the top, let me go to the top again. In the place of n, you add k plus 1. So what will that look like then? You'll say it's k plus 1. This is now in the place of the n. Remember, it was n plus 1. So I'm just writing this here so that you can see where it comes from. In the first n, you write n k plus 1. In that n, you also write k plus 1, and then plus 1. Okay, and if you simplify that, it is k plus 1 and k plus 2. Okay, now let's start now with the left hand side. Remember, we need to prove the left hand side is equal to the right hand side. Let's start with the left hand side. That is going to be 2 plus 4 plus 6 plus, and you continue like that. 2k is what we have here, but we are going to add the k plus 1th term, because that's what we want to look at now. So it's k plus 1. Now we know 2 plus 4 plus 6 plus 2k is equal to k and times k plus 1, and that's what we had at step 2. So you just replace this 2 plus 4 plus 6 plus k with k plus 1, and this will be the same for all your proofs. Okay, and this will then be k plus 1 plus 2 k plus 1. Okay, then but we're not at the right hand side at the moment, because we need to get to k plus 1 times k plus 2. But what we can do is we can factorize this. We can take k plus 1 out as a common factor, and then you're left with k plus 2, and this is equal to the right hand side. Therefore the left hand side is equal to the right hand side. And now step 4 is your conclusion. This is also an easy step if you have done all your steps so far. Then this is just a normal statement you need to write down. So if the statement is true for n is equal to 1, that we proved. Now we said if it is true for n is equal to k, then it is also true, true for n is equal to k plus 1. That's what we showed at step 2 and 3. We showed this n is equal to k, and then it will also be equal to n is equal to k plus 1. And so if it's true for one natural number, it will be true for the next natural number. And the conclusion, and then it will be true for all natural numbers n. There you have it. That's how you do the proof with mathematical induction. And remember, this proof only works where you deal with natural numbers, where the n can be a natural number.